Hello, everyone. My name is Johannes Lehmann. I work at Cornell University in the School of Integrative Plant Sciences, and I'm very glad and grateful to the organizers that they brought us together today, even if that can only be remotely. But I look forward to the discussions later in this program. I'm trying to walk you through a story in 4 chapters around biochar science and implementation, and touch upon climate change, mitigation, soil health, and other environmental quality aspects. Biochar is what I would call a system rather than a material. And that means it has several moving parts. We need to look at from what we make biochar, the biomass, whether that is a crop residue or an animal manure or human manure, whether that is purposefully grown material or other byproducts. We need to look at the products, the gaseous products and liquid products that we might generate, whether that is for energy generation or other bioproducts, and of course biochar as a soil amendment, which I will focus on, but I acknowledge that there are by now many other uses that are environmentally relevant that can be looked at. But in today's discussion, I will focus on its purpose as a soil amendment. There are, in general, 4 different entry points that one might look at in such a system. Underlying the biochar benefits or effects is its soil improvement that I will focus on. But entry points on waste management are equally important, as well as the opportunities for energy production. And of course, looking at the mitigation of environmental challenges such as climate change and water pollution. Bracketed by social and financial benefits, without such a system would hardly be sustainable. In this chapter 1 that I would like to go through, I want to focus on biochar as a soil amendment. And I'd like to distinguish between biochar as a carbon product and as a nutrient product. As a carbon product, the persistence of the organic carbon is important, but also important is what kind of surface properties and amounts there are that can interact with gases and liquids, and what kind of form of carbon the biochar has to serve as, for instance, an electron shuttle. This will affect greenhouse gas reductions as well as carbon sequestration, and these are 2 different things that I would like to highlight in a little bit. They will, of course, affect soil health as any organic matter would, but also pollution reductions, soil remediation, use as an inoculant carrier for beneficial microorganisms, or signaling between plants and the rhizosphere microbiome. As a nutrient product, we increasingly recognize that biochars exist and can be made that are highly enriched in nutrients, and therefore nutrient availability becomes an opportunity for crop production. The transformation of potentially harmful materials such as pathogens and denaturing of pollutants plays a role, and that can, of course, affect its value as a fertilizer. When we look at crop yield increases, we have by now a much greater appreciation for the diversity of crop effects. The global crop yield responses, looking at the published meta-analysis, hover around 11 to 28% increases, but you can see that there's a huge variation. What such global analysis also obscure in global averages is the fact that there are interesting contrasts that can be mined for useful recommendations. And I would claim that very often it might be more important to understand why some of the biochars and biochar soil combinations are highly successful, and sometimes they're not, rather than looking at global averages. When you do exactly that, looking a little bit and constraining the data set and looking a bit in a specific contrasts, such as done here in a recent meta-analysis of the global data set of all published, in this case, field results with relatively low application rates, then one can see that biochar alone has rarely a beneficial effect on crop yield. But if biochar and inorganic fertilizer is added together, that results in a significant crop yield increase here by about 50%, which is about double the amount of crop yield increase that is generated by just adding inorganic fertilizer. And that is an important message, because that means that biochar is as effective as an inorganic fertilizer in increasing crop yields when added in combination, but not alone. Caveat, of course, this is for the global data set that is available at present, but it affords us an opportunity to look at this more closely. Another important point is that it seems that alkaline soils react differently than non-alkaline soils, but also in alkaline soils, as you can see here, with initial pH of above 6.5, biochars that have a pH of less than 9 still generate a significant increase in crop yield in the global data set. However, if high pH biochars are added to high pH soils, that does not generate a crop yield increase. These kind of more specific analysis of crop yield increases also show that the statement that biochar only improves soil fertility in acid tropical weathered soils is not correct. In the chapter 2, I would like to move from the biochar as a soil conditioner also to biochar as a fertilizer, and look at the waste management opportunities. We have used waste as fertilizers for a long time when we look at night soils, but also we have appreciated, for instance, slaughterhouse wastes and bone fertilizers for quite some time, since the early 1800s, and obviously have had an industry for a very long time. We've seen a historic decoupling of the nutrient cycles over the past couple of centuries from pre-industrial agriculture, where we now are not only faced with a broken nutrient and energy and carbon cycles, but also with increasing challenges in water, soil, and air pollution. And the question is whether biochar technology can contribute to recycling nutrients and carbon, but specifically nutrients that would otherwise cause an environmental pollution and are a scarce resource. Such smart recoupling of nutrient cycles can, for example, occur in dairy manure, or in general in animal husbandry, where under typical scenarios we see unwanted contamination of our water resources, causing harmful algal bloom, whereas a pyrolysis system might afford the opportunity to mitigate these water resource impairments through a three-pronged approach. One is to use biochar as an absorber to retain phosphorus that is in soil using low phosphorus feedstocks and biochars, or convert the high phosphorus containing feedstocks such as animal manures into fertilizer and partly immobilize nutrients through that process, or the most effective is to obviate the entire problem by adding such a fertilizer into a value-added fertilizer stream and transporting it out of the watershed altogether. This is also not only a problem with would not only solve a problem with harmful algal bloom, that now also in upstate New York we have an issue every year that our lakes that are huge income generation for the local industry has to close due to harmful algal bloom, but also because we are facing at some point a peak phosphorus that is a finite resource for agriculture. We don't know when this will happen, but it surely will happen at some point. For New York State, we realize that that there are quite a bit of phosphorus in manures. Here, dairy manure, 9,000 tons of phosphorus per year are applied in comparison to New York State fertilizer sales of about the same amount of phosphorus per year. So those are opportunities to more judiciously utilize our resources, and pyrolysis might be one way of achieving that. We now know that the dairy manure shows no contamination with heavy metal pHs and other toxins that we could find in New York State. Also, any pathogens, hormones, or antibiotics are typically denatured. We can make a high-value potting mix that reduces mass and volume by 96%, and generate a value calculated about just under $2,000 per ton, which generates quite a financial potential for farmers and retailers in New York State. What is especially interesting is that some of the nutrients that are in biochar that is produced from dairy manure are better available than it was in the original manure, and it is less leachable. So while it is better available for a plant, it seems to be less mobile, which is a bonus both for the environment and for nutrient management. Another nutrient management aspect on farms in a dairy or animal husbandry context is the potential absorption of ammonia gas to biochars. Highly oxidized, low nutrient biochars have been shown to be superb absorbers for ammonia gas, creating a high nitrogen compound with up to 18% nitrogen. That's greater than any manure would have, while mitigating odor in animal husbandry, which can be a main issue in dairy farms. In chapter 3, I would like to briefly mention the variation and diversity of energy generation through biochar and pyrolysis that encompasses both, of course, direct heat generation as well as gaseous and liquid compounds that can be generated. Very versatile and energy generation that is possible. One aspect that has to be very clear that every carbon that is retained as biochar is of course not generating bioenergy. When you look at the full life cycle assessment of the energy generation, you realize that per unit feedstock in a biochar pyrolysis system, about half of it, little under half, may be a net energy generation, and about the same amount will be sequestered in biochar. That creates a trade-off between energy generation and biochar yield. So the more biochar you are generating, necessarily the less energy you are generating. But there's a wide variation in these trade-offs, and there are not always straight lines. So there is some optimization that is possible. Fast pyrolysis typically generating more energy and less biochar, versus slow pyrolysis generating more biochar and less energy. In chapter 4, I would like to mention biochar climate mitigation, highlighting 3 entry points that are really important to realize. The first one being, of course, if energy is generated, that energy can, in a sustainable system, if the biomass is renewable, generate bioenergy and offset fossil fuel emissions. This is very similar to any bioenergy system. However, the second one being both a carbon dioxide removal and total emission reduction through pyrolysis, because the material that would otherwise have decomposed very rapidly, such as leaves or manures, within a year emitted the same amount of carbon and potentially nitrogen and methane gases, would remain in soil for much longer period of time, and is recognized as practically annihilating N2O and methane emissions that would otherwise occur if that biomass had been added to soil. In addition, and that's probably the most interesting and aspect that sets it apart from other systems, is that biochar added to soil may have additional emission reductions of the carbon that is already in the nitrogen that is already in the soil, as well as increased CO2 capture through greater crop production, plant production, as I explained earlier. That other 20% increase in crop yield and biomass production generates, of course, an additional sink in carbon. For this to be workable, the persistence of biochar is really key. And when you pyrolyze organic material, you're fusing aromatic rings that are more persistent in a soil environment, and by several orders of magnitudes potentially. We now have a growing number of studies that are looking at the persistence of biochars, and you see here that those that are using longer term observations generate typically mean residence times of above 500 years. This has led to a new IPCC guidelines for greenhouse gas accounting that is relying on these trials to look at the fraction of biochar remaining after 100 years as a function of pyrolysis temperature. And you see that for low temperature biochars, 65% of biochar will remain after 100 years. This number rises to about 90% for biochars created above 600 degrees Celsius. Such a approach is consistent with our knowledge that higher pyrolysis temperature creates higher condensation and therefore more fused aromatic rings and therefore greater persistence. It also is an opportunity for monitoring this practice of conversion rather than the presence of biochar in a soil after a certain time. And that is what entered the IPCC guidelines in 2019, which hopefully can be taken forward in other methods. One would need to go beyond an accounting of just biochar, as I mentioned earlier. It is what underlies the basic principle, but there are other emissions that are generated and other emissions that are avoided along the entire life cycles. Some of those might be conservatively assumed to not generate certain emissions and be therefore ignored in a full accounting, but they need to be considered in the initial calculation. Here's such a life cycle assessment looking at agricultural waste products as well as purposefully grown biomass, switchgrass, as well as yard waste. And what you see here are the reductions in the lower bars and the emissions on the higher bars, and the net is apart from one scenario where we assumed large indirect land use change through replacing food crops, always a negative number, which indicates that these are sequestering carbon and reducing greenhouse gas emissions. What you also see is that the largest part, typically, the single largest emission reduction is delivered through what's blue here, which is the biochar that persists over a long period of time. So that underlies much of the emission reductions that you can see, and constitutes also a carbon dioxide removal, not just an emission reduction. In this analysis, crop growth and soil, some of soil greenhouse gas emissions are not included as a negative emission, as a sequestration or additional greenhouse gas emission reduction. And in that such a scenario, the total balance is about equivalent to if we had only generated energy through combustion and not sequestered any carbon and had any other ancillary greenhouse gas benefits. So the soil emission reductions and photosynthesis of greater crop growth is important to consider when claiming to have a greater greenhouse gas emission reduction with biochar than with an energy generation. However, this also assumes that energy can be utilized, and as we are painfully aware, that is not always the case. Very often emissions are generated in places where energy generation and capture is not possible. A couple of examples from high nutrient containing biochars here with poultry litter processing and different upgrading possibilities that generate various environmental benefits, whether related to human health, ecosystem quality, climate change, or resource depletion, in comparison to land application that you see here on the right. You see different approaches: slow pyrolysis, fast pyrolysis, gasification, different hydrothermal and supercritical conversion processes. What you see very easily is that all of them have a greenhouse gas emission reduction and a benefit, and that slow pyrolysis has the greatest negative emission balance. But there are big differences with resource depletion, especially when considering that some approaches generate less energy than others and necessitate then greater energy generation from fossil fuel potentially. Environmental benefits are also concern nutrients, as I mentioned earlier, but they have a distinct transportation and spatial aspect to it. Here you see for the example of the state of Georgia in the US, a regional mismatch of resources and need. Poultry litter production here in these different counties that are blue are much greater by an order of magnitude or more than in other counties. However, biochar demand according to phosphorus needs of the same state is very different, where most of the phosphorus need is actually down here, where there are almost no poultry litter production. But looking at the distribution opportunities and conversion opportunities, one may come up with different scenarios of pyrolysis units and size of pyrolysis units, here shown for slow pyrolysis in comparison to fast pyrolysis. and looking at the unit emissions of such systems versus the profit. And you can see that there are different relationships here. If we take the one that here's scenario B, that actually has the greatest greenhouse gas emission reduction and the greatest net carbon dioxide sequestration. Sorry, it's the greatest net carbon dioxide sequestration opportunity, because most of the carbon is sequestered in biochar. We see an optimization opportunity here, how to arrange biochar plants in this state to reduce the costs, maximize profits, and maximize carbon sequestration. But those are opportunities that need to be discussed and optimized in each case individually. Some take-home messages. The crop production increase is a quantitatively relevant aspect of biochar systems for soil carbon sequestration and greenhouse gas emission reductions. And those are two different things that need to be considered. The crop production increase, it has to be and will remain the main incentive for biochar adoption in terms of soil amendment, because only with that aspect we will also have the greatest emission reductions. The nutrients have been a bit ignored in the past, but are potentially a very important resource and provide also environmental benefits through better water quality. Persistence in application are opportunities that are now afford the option to monitor practice rather than presence, as seen with the new IPCC guidelines. There are greater life cycle emission reductions than soil carbon accrual alone, which has to be looked at individually and optimized. And again, crop production plays a big role in that aspect, and especially when looking at the spatial aspects that are critical for this optimization, to make sure that crop production is maximized while resource use is optimized, and that requires regional and global optimization to cater to the specific site conditions. And with that, I'll thank you very much for your attention, and I look forward to the discussion. Thank you very much.